Then let me share the screenshot. Okay, can you see the screenshot?
Yes, I can see it.
Yeah, can you see that clearly?
I can see your notes and yeah, the highlight.
Yeah, right. Okay. All right. Okay. Let's see. Okay, so hello everyone, and then this is the last day of this book club. Yeah, cause this is the today I'm gonna try to cover the last chapter of this book, like a hands-on machine learning with R. So last chapter is about the model-based clustering. Cause in the last 2 weeks we actually cover about the clustering analysis, such as k-means clustering, and also last week we actually cover about the hierarchical clustering. But those two clustering technique actually about based on the some of the our heuristic kind of approaches, which means it is totally dependent on our intuition or our insight or our background knowledge. Depending on those kind of knowledge or background, those analysis strategy gonna be determined, right? Because it's a very what is called a heuristic kind of approaches, and also interpretation of the result is a very heuristic approaches because it is more dependent about our intuition or our insight about the way we looking at the data set and then the way we looking at the result, right? It is totally dependent on our background knowledge or our kind of insight or intuition. But in case of the model-based learning, this is the more like about the more statistical approaches, more focusing on the optimizing, statistically optimizing the result based on the some set of the statistical method. So as you can see here, this is also one of the big way we can actually do about the model-based clustering is what is called the Gaussian mixture model, like a GMM, which is this. So we're gonna cover this one actually throughout this chapter. And then this one actually allows us to the not only to give us to the statistical kind of analysis, especially for the probability of the each observation is belonging to the each cluster. Okay. And also at the same time, this kind of approach also allows us to do the uh, identifying number of a cluster based on model optimization. Okay. So based on the model optimization, like through the sum of the set of the statistical analysis, we can also determine about the number of clusters within these kind of modeling approaches. Okay. So here is the kind of a prerequisites about we're gonna also use the M cluster in this case. And then using the Geyser data based on the MS package. And then now let's talk about this model a little bit deeper, okay? Because a GMM model, like a model-based kind of a clustering is kind of like all of these data actually coming from the mixture, what is called the mixture of the underlying probability distribution. What does this means is actually whenever we have some of the outcome like this, these kind of outcome actually belonging to the some of the distributional kind of a curve like this. Like when we try to do the categorical kind of analysis. So we can say about these are all of these kind of a different category. And then we actually have observation like this. Okay. So that's what this one calls. Because each data and observation is actually coming from this kind of underlying distribution. At the same time, maybe assuming that if we have this kind of our data distribution curve as an outcome, actually this kind of a distribution outcome actually comes from the set of these kind of outcomes, smaller distribution outcome. Okay, so each of these kind of outcome has a very homogeneous within the cluster. So each these one actually we can actually say about the clusters. Okay, so depending on so each of the data set actually coming from these kind of a mixture kind of a outcome. That means we can get the final kind of a whole distribution outcome. Because this entire distribution outcome actually come from this set of the optimized cluster, optimized probability distributions that belonging to the each that actually represents to the each cluster. Do you understand what this means? Yeah, you can actually thinking about all of these small kind of a distribution curve as a number of clusters we can actually thinking about. And then another thing we can also talk about is this model actually depending on about the multivariate normal distribution, which actually contains about these are the set of the like I would say set of the independent variable like features. These are the features, and these are the features. And then we can actually draw about each correlation, variation, covariance, I mean, covariance as a matrices inside here, right? These are what is called the covariance matrix. That's what this one is about. And then based on this kind of a covariance, we actually assuming that this one actually has a normally distributed curve, set of the normally distributed probability curve with the mean of the mu, and then variance is the sigma, one of these kind of a variable. Okay. So based on this kind of assumption actually allows us to the differentiate like a grouping the set of the outcome into the some a few cluster, which is like here in the figure 2.22.1. So as you can see here, these are the kind of we can say about the one cluster because it's actually clustering together, and then this kind of a covariance between these data is pretty small compared to this one to this one. It's a much closer, right? And then another one is this one for the as a cluster, because these are the actually cluster whose variable is whose covariance between the data is quite small. At the same time, these are also quite small. So in here, we have three different clusters, right? Depending on the X and Y kind of a scatter plot kind of distributions, like probability of the cluster, and then number of a cluster can be determined based on these kind of observe the kind of a distribution outcome. Okay. And then based on these kind of assumptions, we can actually draw some of the good insight about the good based on these kind of insight, we can actually develop the code about the clustering, like a model clustering. So by using the M cluster function, and then a G actually, this one actually means about the number of cluster. And then this one actually means we actually using the Geiger data set, and then we actually thinking about the three components, three cluster of the data. And then when we plot the result, we can get this kind of three different plots. And then also you can see this kind of a three different plot kind of a curve, like a uncertainty kind of curve. So actually this kind of a clustering actually shows that about the uncertainty is a kind of a very small within this cluster. And then at the same time, you can also thinking about the X is the weighting and then the Y is the duration as a kind of a outcome. So you can actually compare with at the top of this plot with this, and then it's the same density and uncertainty plot. And then uh and then we can actually try to identify the observation with the high and low cluster uncertainty. And then this one actually try to give us to the more distinctive clustering outcome. Okay. And then how we can, another thing we also have to keep in mind when you try to do the model-based clustering is what is called the covariance types. In this one is actually have a clustering and density of actually very proportional into the shape or size. Because as you can see here, this one actually type of the shape, example of the shape of the size, shape and sizes, because this one actually has a size, right? At the same time, it also seems to have a quite circular based kind of a shape. So shape and volume is actually size, and then orientation sometimes is a kind of a very important about how we can grouping our observations into the several clusters. So there is actually 14 different variations in the M clusters actually thinking about all of these things. Okay. Because family is spiritual means like a circular one, and diagonal is the more like a directional kind of things, and then a general is more like a complex or more kind of a not defined kind of a curve, and then also volume, and then a shape, and also orientation is a kind of a axis, like there is any kind of a direction to it or variable, and then these are the kind of identifier has this kind of a name in it. And then when you actually saw some of the plotting outcome to determine the what kind of grouping shape and volume and type we have to choose to get the optimized clustering result. Okay. So these are the actually basic example about the clustering pattern, right? So like this EV has actually kind of a very spiral kind of a directional kind of a curve, and then EII is the most typical kind of a separation of the clustering outcome, right? So a whole different kind of a clustering can be considered based on these kind of a 14 different different searching, and then M cluster actually automatically testing the modeling fit, clustering fit, depending on those 14 types of the cluster, and then automatically find out which clustering type is the give us the better result. So these are what is called the model selections in here. Okay. So whenever we have a kind of a summarized our outcome, all we can have to see is this outcome, like a BIC, like a Bayesian information criteria outcome. This one actually one of the good criteria to the choosing our modeling selection. So this one actually close to the zero. That actually means that it is a very good goodness of the fit is very good. Okay. So it is actually close to be one gonna be the better model. And then a clustering table means we have three different clusters in this case, like three clusters in here. So this is actually basic outcome from the code in here, because we actually set up the number of cluster as a three. And then when we summary those results, we can actually get that modeling fit and then a clustering outcome. And then also what kind of clustering shape family gonna be we can choose. And then this BIC actually has the result of this clustering pattern outcome. Okay. We can also say about the without G is null. In this case, we can actually let the computer choose the optimized kind of a model. So whenever we actually do this kind of things, computer actually automatically choose this one gonna be the best one. And then when we choose these approaches, what's the BIC outcome, which is the much close to the zero. So that means it is a much better fit when we have four clusters. And then we can also drawing about plotting about this kind of a BIC outcome. Okay, like this one. The first one is this. Okay, and then as you can see here at the top, like a VVI, it is very hard to see, but BVI is one of the top kind of outcome when it has the four in here, and then that's the reason why computer chooses the very largest BIC outcome close to the zero, and then based on that, another two plot, which is this and this, yeah, actually represents about the number of how clustering gonna be formed in this case. Okay, these two. Okay, so that's the how this one is about. And then now is a 22.5 is a kind of a, we have a kind of an example for the basket example about the grouping our transaction basket outcome. And then this one is also can be possible to do that, like based on the M cluster, and then we can actually set up the number of cluster, testing the number of cluster between 1 up to 20 cluster, and then when then M cluster optimizing our clustering modeling result, and then when we summary this outcome, we can say that okay, EEV gonna be the optimized uh cluster shape and volume. And then at that time, when we choose the EEV, the Bayesian information criteria is this kind of number, which it shows about the goodness of it. And then our cluster, number of cluster for the optimization is the 6 clusters. And then we can also easily can see that when we plotting that Bayesian information criteria outcome as a plot, we can also see that in the cluster, when the cluster is a 6, and when we choose the EEV kind of a clustering mechanism, we can have a maximum BIC value at the top. So that's our number of cluster with the clustering mechanisms. So it's a very simple outcome once we have the data set, right? And then it actually easily optimizing our number of clusters and then our modeling goodness of fit based on these kind of probabilities and likelihood of the model optimizations. Okay. And then when you see about these kind of clustering outcomes, we can actually see about the in case of the C3, there's only extremely low value and high value exists. That means that there is actually almost no in between values. That means this one is a very most compact kind of a cluster. Okay, because its cluster size is very, very small, and then a very, very minimum covariance between the data in this case. Okay, whenever we have a lot of middle value in here, that means cluster gonna be gets larger. Okay, and then it is actually larger covariance outcome. Okay, so that means clustering shape is a little bit bigger compared to the C3. Do you understand what I mean? And then also it's the same thing about we can actually thinking about the uncertainty curve. We can actually see about in case of the number 2, there is a lot of uncertainty things coming up in here. That kind of having a lot of uncertainty in within the cluster means that this C2 actually have a largest cluster. At the same time, this is actually largest covariance within the data. At the same time, this C2 actually have a kind of a very, very loose kind of a classification outcome compared to the number 3 and other cluster. Because in this case, actually cluster 3 does not have any plot because cluster 3 actually have a very clear and compact kind of a clustering outcome. So in this case, we don't have any kind of uncertainty in here in case of the case 3, cluster 3. So that means cluster 3 is a very, very good differentiation. Okay, but in case of the cluster 2, it is very hard to understand about the characteristic of the cluster 2 because of there is too many uncertainty data in this case. Also, maybe cluster 6 or cluster 5 also pretty the same pattern. Okay. So actually, whenever we have a lot of uncertainty outcome within the cluster, that means the harder we can understand about the characteristic of that clusters. Okay. So as you can see here, when you're looking at this kind of a cluster 2, and then when we're looking at actually what is the cluster 2 consist of, is mostly these are the kind of mostly clustering belonging, these kind of item actually mostly belonging to the cluster 2. But the thing is that there is also a lot of other items belongs to this group. So that means it is a little bit hard to understand about exactly what this cluster represents. So this is all depending on about our intuitions or our background knowledges to identify or infer these kind of characteristics. Okay, but the thing is, compared to the k-means and hierarchical clustering, modeling based clustering is more allows us to optimizing our outcome much better, and also model based clustering give us about the more statistical outcome that supports our insight or our rationale of the classification outcomes. Okay, so that means compared to the other two clustering algorithm in the previous chapters, model-based clustering is a more statistical based kind of approaches to get this kind of a clustering analysis. So it is very computing intensive kind of a process, but it is worthwhile to try that out because it definitely gives us about a very good and solid statistical outcome based on the optimization of the clustering. Okay, so this is the this is the end of this chapter 22. And then, do you have any questions so far? Anything?
Okay, one second. Can you hear me? Answers?
Yeah. I
Yeah,
can hear you.
yeah.
Yeah.
Great presentation. Just
Uh,
to add, some of the new, kind of not new, but all are new techniques that also can be used to visualize,
mm,
on label data. One
yeah,
of them
right.
is called TSNE. Okay, TSNE. That's kind of the
Uh-huh.
an old one, but also it's a good technique to try to visualize these groupings. To see
Mhm.
there's any pattern around them.
Yeah.
And then also there's another one which is a newer one, okay, which is UMAP. And
Mm-hmm.
also UMAP, the good thing is that TSNE is slower, in terms of the calculation. It's a slower
Mm-hmm.
algorithm. UMAP
Yeah.
is a speedy one.
Mm-hmm.
So it would be great, to see, what is the output of these data sets that we're using,
Mm-hmm. Yeah.
utilizing testing and UMAP, mainly for visualizing the graphic. Okay, I
Mm-hmm.
have used
Mm-hmm.
UMAP, a couple of times, and it gives pretty good, pretty good results. Okay, in terms of visualizing,
Mm-hmm.
the clusters. For example, if you choose a number of clusters based on silhouette or gap statistic
Mm-hmm.
or elbow, you can then check with UMAP to see, if the clusters are grouping correctly. Okay, in terms of the graphic plot. So that would be my 2 cents here.
Yeah. Yeah. And also, I just wanted to point out is in here actually, in case of the data about the optimization, it actually has about the volume and shape and orientation. And also, maybe if I wanted to point out is if you have a time series, like a growth curve data, in this case, you can also say about the maybe like this, and then in this case, we can actually grouping this one is cluster 1, this one is cluster 2, right? So maybe this one also gonna be related to about the shape or maybe some of the orientation like the trend outcome characteristic. Actually, this one is also kind of a one of the technique can be used for our analysis because when we have this kind of a time series growth curve data set, and then when we try to do this one, maybe we can also try to do the growth mixture model. This one is also represents about the GMM, but this one is a more like a time series analysis, like based on the shape of the growth curve, we can actually grouping the number of clusters. There is also algorithms that allows us to do this. And then another thing I also wanted to point out is other than this kind of a shape, at the same time, we can also thinking about some of the maybe some specific independent variable can be defined to as a kind of a weight variable that affects to this kind of a outcome. Okay. So that is actually kind of another way we can do, because this one is actually what I use for the my doctoral dissertation. Because in these cases, maybe we can actually grouping this kind of a time series curve based by using this kind of a gross mixture model. There is actually two different kind of approaches. One is the multi-level kind of a modeling approaches. The other one is the structure equation modeling framework. So by using these two kind of algorithm, we can also grouping these kind of time series grouping, time series growth curve outcome, like these kind of a model-based clustering. After that, I also suggest is whenever we get to the point about the finishing some of the clustering outcome, so that means what we can get is in the table, maybe observation 1, 2, 3, etc. We can actually get the kind of a result about okay, this one is the cluster 1, cluster 2, and cluster 3. Assuming that we can actually have a 4 cluster, that means we can actually get the sum of the probability estimation as a continuous variable. So likelihood over each observation belonging to each cluster. Okay, this kind of a probability can be used as some set of another outcome variable inside another regression model after this kind of a clustering analysis. If we need to explore much deeper about what's the main characteristic about this classification outcome, maybe multi-logic or some of the regression modeling approaches can be possible. Okay, I think that's it. So, any questions so far?